Chapter 4 material. First thing that we talked about with regard to Chapter 4 was this concept of aromaticity and classifying compounds as being either aromatic, non-aromatic, or anti-aromatic. And lastly, we can determine the number of localized and delocalized electrons in each structure as well. All right, so everybody take a second and let's copy down these examples, give you a little bit of time to work through them, and then we'll go through them together. All right, so again, copy down these problems. Take a few minutes to try to tackle them on your own, and then we'll go over them together here. let's go through them. So first of all, like as an instructor, I'm very much more like of a skills-based kind of instructor. I like teach you a skill and then I expect you to be able to demonstrate that skill, right? Not so much on like the trivia kind of aspect of a course, like who found an electron, that type of question, right? Very much so more skills. We learn a certain skill such as how to classify compounds, etc. But qualitatively, it's kind of important to remember what's going on here with our aromatic compounds. So if I go back here, remember, I've sort of brought up this slide a lot because it's a good indication of what's exactly happening. So for all these sorts of things, it's a good idea to have like this quintessential example going on in your head. And for aromatic compounds, that should be benzene, right? We know that benzene is aromatic. And what does that mean exactly? Well, benzene's got each of its carbons has this p orbital sticking up, right? And all these orbitals are conjugated. And so the electrons in those orbitals can kind of spread themselves out, okay? And that is the nature of this aromaticity, the spreading out of those electrons across the ring. So again, for those orbitals, which is, an orbital is an electron's where an electron lives, we say that those orbitals are conjugated, okay? And the electrons that are spreading themselves out are what we call delocalized. Okay, so very closely related concepts. When we talk about something being conjugated, we're talking about those orbitals. And when we talk about electrons being delocalized, we mean that they're spreading themselves out across those orbitals. Okay? So when we go here and we're talking about classifying compounds as being aromatic, non-aromatic, anti-aromatic, we have these two rules, right? You need to follow two rules in order to be aromatic. Rule 1 is you have to be a fully conjugated ring. Right? Each one of those atoms in that ring needs that p orbital sticking up that those electrons can diffuse themselves around through, that they can delocalize through. And then 2, you had to have an odd number of electron pairs. Those were our 2 rules. If a compound satisfies those 2 rules, then we consider it to be aromatic. All right? If it violates rule 1, what do we call those? Those are the non-aromatics. And if it violates rule 2, what do we call those? So those are the anti-aromatics. Okay? So that's the name of the game here. We're going to go through and look at these rings and see if they're fully conjugated. Then we're going to count the number of electron pairs, see if it's odd or even. And from there we can classify compounds as being aromatic, non-aromatic, or anti-aromatic. Okay? So going here, what do I mean by a fully conjugated ring? So how do I identify whether one of these atoms is part of a, quote, fully conjugated ring? So it would have to either be part of a double bond, have a positive charge, or maybe be a lone pair. We'll talk about why we have that maybe qualifier in front of there here in a second, but let's do some examples first. So again, we're going to go around our ring and we're going to look at each atom and determine whether it's a fully conjugated ring, right? So are these atoms a part of a double bond or have a positive charge and maybe a lone pair, all right? So let's go, first example here. We're going to start going around and looking at each atom, right? So, okay, this atom here is a part of a double bond. This one here is a part of a double bond. So is this one. So is this one. But now I get to this one, and it messes it up, right? This carbon right here at the top messes up my ring's conjugation. This is no longer a fully conjugated ring. So this would be non-aromatic, right? Violates that first rule. So then I can go out, down and count the number of delocalized pi bond electrons. What do I mean by pi bond? A double bond, right? So a double bond consists of a sigma bond and a pi bond. Importantly, those pi bonding electrons are the one that I pictured here that can delocalize around and around that ring. Right? Those are what we call pi electrons. So how many delocalized pi bonding electrons do I have in this molecule? 4, right? So even though that ring is not fully conjugated, those two double bonds are still conjugated with one another. The electrons can move back and forth. They can delocalize across those 4 atoms. They just can't do it for the full ring, right? And that's what makes it aromatic when it's a full ring. And then how many delocalized lone pair electrons do I have? I got no lone pair electrons in this compound at all. Okay. So now, moving on to our next example here. Again, I'm just going to go around the ring and make sure that it's fully conjugated. Again, these 4 are a part of our double bond. And then this other carbon is a carbocation. That also has that empty p orbital that the electrons can diffuse through, that they can delocalize through. So positive charges don't mess up our conjugation. So this is indeed a fully conjugated ring. Check, check on rule 1, all right? Now I got to go to rule 2, count the number of electron pairs in this ring. I have 1, 2. Importantly, that positive charge doesn't have any electrons associated with it, right? It doesn't mess up my ring's conjugation, but it also doesn't add any electrons to the ring. So this is an even number of electron pairs, making this compound, what? Anti-aromatic. Okay. Again, in terms of the number of delocalized pi bonding electrons, I still just have those 4. And I don't have any lone pairs in this compound, regardless of whether they're delocalized or localized. Okay. So now going on to my next example here, again, seeing if I have this fully conjugated ring. So now I get to this situation of a lone pair. All right, and again, we said maybe lone pairs are conjugated, maybe not. We got to look and count the number of electron pairs. Because this lone pair is only going to participate in this ring if it makes this compound aromatic. If not, the atom's literally just going to point the electrons in a different direction. Right? Instead of putting them towards that ring, it's going to point them outwards. Right? So it's almost like these lone pairs get to choose whether or not they're going to participate in the ring. And again, they're only going to do so if it would make it aromatic. So in this case, I have 1, 2. This lone pair would give me 3 pairs of electrons, an odd number of electron pairs. So it's going to do it. It's going to participate. So we got a fully conjugated ring with an odd number of electron pairs. So this compound here is aromatic. Okay. Again, it's got those same 4 delocalized pi bonding electrons, but now I got to classify this lone pair as being either delocalized or localized. Which one is it? Delocalized, right? It's participating in that ring. So I got 2 delocalized lone pair electrons and 0 localized lone pair electrons. Because it's participating in that aromatic ring, right? It's going to put itself, that pair of electrons is going to be added to the ring. I'm counting that as one of my odd number of electron pairs, right? Because it's aromatic, that means that lone pair is participating, means that those electrons are being spread out across that ring. They're being delocalized.
Okay, it's not, okay.
Localized would mean that they're not participating in the aromatic ring. Like delocalized is like spread out, not one location. What's up?
The negative charge, does that do anything to it?
It means that there are electrons there. It means that we count those electrons. So the lone pairs are either going to be on a carbanion, as in this case, or on an oxygen or a nitrogen. So in this case, that fact that there was that lone pair is because of that negative charge. All right, so this one we have a similar situation, but instead of being a carbanion, it's an oxygen that has that lone pair. So again, I'm going to go around, make sure my ring is fully conjugated. Again, I get to this situation of this lone pair. It gets to decide whether or not it's going to participate in the ring. It'll only do it if it makes it an odd number of electron pairs. And indeed, that will. So this compound is also aromatic. Importantly, with regard to oxygen's got those two lone pairs, right? Only one of them will ever be able to participate in the ring. It can't put both of them in that ring. So I'm only ever looking at one of those two electron pairs. The other one just has to be localized. All right, this has to do with like the geometry of how those orbitals work. Basically, it can't put both of them into the ring at the same time. It's just not possible. So I'm only ever looking at one of those electron pairs to figure out whether or not it's going to participate. So this is aromatic. I have those same 4 delocalized pi bonds. Now in terms of delocalized lone pair electrons I have, and how many localized lone pair electrons do I have? Also 2, right? So just to be clear, this pair of electrons here, we're gonna, well, I guess I can use the same color. We're gonna say participates in the ring, so that's my delocalized lone pair. The other one will not, that's my localized lone pair. For these like fused rings, I know that this is where things kind of look a little bit crazy, but we're still going to play the same game, right? We're going to go around the ring looking at each atom, determining whether or not we have a fully conjugated ring. So it really helps to just like put your pencil on each one of them as you're going through to determine, right? So again, this one, part of a double bond, so is that one, so is that one, so is that one, so is that one, right? So I know that these carbons that are at these intersections can be kind of confusing, but you're just asking yourself the same question as we were before. Is it a part of a double bond? Does it have a positive charge, etc.? So now this one. So now the only one that I can't determine yet is this nitrogen, because it's got this lone pair. So again, maybe this lone pair is going to participate, maybe not. It'll only do so if it makes that ring aromatic. So I got to go through and count. 1, 2, 3, 4. If I count this lone pair, it would be 5. So that would be an odd number. So indeed, that nitrogen's going to put this pair of electrons in the ring, making it aromatic. All right, now how many delocalized pi bonding electrons do I have? So now I got 8. And how many delocalized lone pairs? And then localized lone pairs, I got none. Okay, so everybody take a second, if you hadn't already gotten around to it, try to do this last example here in light of what we just discussed with all these previous examples. All right, who thinks it's aromatic? What about anti-aromatic? And what about non-aromatic? So this is actually non-aromatic. Let's see if we can convince ourselves of that real quick. So again, I'm going to play the same game where I'm going to go around the ring, make sure that every atom is able to participate. I got this one, and this one, this one, this one. All of these are part of my double bonds, or have a double bond associated with them, rather. But then I get to this one over here. And this is the one that messes everything up, right? This green carbon right here, it's not a part of a double bond. It doesn't have a positive charge. It doesn't have any lone pair on it. So this is what messes up my ring's conjugation and is going to make this compound non-aromatic. I do not have that fully conjugated ring. I still have these 6 delocalized pi electrons. But then these 2 lone pairs on my oxygen, are they going to be localized or delocalized? Yeah, because this compound's non-aromatic, they can't participate in the ring. So I have 0 delocalized and 4 localized lone pair electrons. All right, so that was sort of skill number 1 that we got from chapter 1, was to be able to classify compounds as aromatic, non-aromatic, or anti-aromatic using those 2 rules. All right. The rest of the chapter.
Make it a little bigger. Sorry.
That's as big as it gets.
Okay, cool.
All right, the rest of the chapter revolved around these same 6 reactions here. All right, so actually take a second and let's copy this word bank here, or this reagent bank, because then we're going to use these reactions over and over again here. Remember these R's. R means any number of carbons and hydrogens. All right, and so importantly, again, R you're going to replace with any number of carbons and hydrogens. So this is what you'll be given on the exam, is this bank of reagents here. If you utilize one of those 2 reagents, you're going to have to explicitly tell me what R is, right? Is it a methyl group? Is it, 2 carbons? Whatever it is, you're going to have to tell me explicitly what it is. All right, so first, I guess, would just be, can you predict the products of various reactions? All right, so we need to know what those 6 reactions do. They're always adding something to the ring. They're actually substituting onto that ring, replacing one of those benzene hydrogens with a different functional group. We got to know what those 6 reactions do for us. So going through each of these reactions, these first two, you're just starting out with like a naked benzene ring, right? Just normal benzene here. And again, in each reaction, what you're going to be doing is replacing one of the hydrogens on that benzene ring with something else. You're swapping it out. In the case of using bromine and aluminum bromide, what am I putting on my ring here? Yeah, so this will attach a bromine to the ring. All right, that's what that particular reaction does. Swaps out hydrogen for a bromine.
Just one.
Just one, yep. So even though this is Br2, only have one bromine on that ring.
We don't even worry about all the ring.
Nope. No, I mean, if we were being really good, we would have also HBr as our product, but truthfully, we rarely do we give a crap about what happens to the inorganic product. We really are caring about what's happening to our carbons here. Okay. In the other one, H2SO4 that is fuming, I'm swapping out this hydrogen for, anybody remember? SO3H. Sulfonyl group or a sulfonic acid. All right, if we sort of drew it out, and you can write SO3H, that's fine, but just to sort of see what it looks like. It's that big ugly thing there.
Do you have to draw it out?
Nope, you can write SO3H, that's fine.
If it was like HSO3 with
HSO3 is not, no, you got, it's the sulfur that's actually attached to the ring, so that's why we write it like that. Okay, now for these next one, we already have something on that ring, right? So the question is where does this new functional group that I'm attaching go relative to my existing OH group? Okay, now we have to consider what we call like these directing groups, the directing of these groups. So first of all, we had names for these positions. What are the positions located right next door to whatever's on that ring already? Yeah, these are the ortho positions. If we go one away, these are what we called meta. And then on the exact opposite side of the ring, we called that group, that's the para position. All right, so OMP, ortho, meta, para. Okay, so that's our question. We're going to be putting this, so first of all, with this reaction here, with nitric acid and sulfuric acid, what's my new group that I'm adding on there?
NO2.
Yeah, so I'm going to put on what we call a nitro group, NO2. That's going to go around my ring, right? But the question is where? Does it go in the ortho position, the meta position, or the para position? And for that, I got to look at what's already on that ring. In this case, this OH group. All right? We can classify all these groups that are on the ring as either ortho-para directors or meta-directors. They're all going to fall into one of those two categories. All right, if you remember back, this would correspond to what we had. This slide here is sort of the cheat sheet of all this. Okay? The ortho-para directors are easy to spot because always have a lone pair that's going to be located right next door to the ring. All right, so if you have an atom with a lone pair on it that's right next door to the ring, that's going to be an ortho-para director, including if it's one of these halogens. All right, these also have lone pairs. The only exception to that rule are these alkyl groups here. They are also ortho-para directors, but they don't have any lone pairs. All right, so the ortho-para directors, again, they're kind of easier to spot because you can have these two simple rules. Does it have a lone pair right next door to the ring, or is it an alkyl group? If not, it's going to be a meta-director. We did say we kind of had some common features of our meta-directors. They're usually carbonyl carbons that are connected to the ring. Right? By carbonyl, I mean this carbon-oxygen double bond. A lot of our meta-directors share that feature. But then there's other ones that we just kind of got to know. Our sulfonyl group, the cyano group, and that nitro group, that NO2. And these two, I think, are kind of I don't know. I would definitely star them in my brain to remember them because we know how to put those on a benzene ring all by itself. All right, so these are all our meta directors. So we got to go back to our example. And we got to ask ourselves, this OH group, is it an orthopara or a meta director? Orthopara. Remember, this oxygen is going to have 2 lone pairs on it. So we have this lone pair located right next door to the ring. So when we draw our 2 products, and they will be 2, we got to draw both of them. We got one where my nitro group is in the ortho position, and the other one where that nitro group is in the para position. So now I have chlorine and aluminum chloride. So this is going to be adding a chlorine onto my ring. But again, I got to ask myself, is this an orthopara or a meta director? Which one is this group going to be? So this one's a meta director. Again, you can have those 2 simple rules for is it orthopara. Is there a lone pair right next door to the ring? This oxygen does have a lone pair on it, but that's not what's connected to the ring. This carbon right here that's connected to the ring, right? This isn't an alkyl group, there's not a lone pair, so it's gonna be a meta director. So in this case, I'm going to draw my new functional group in the meta position relative to my existing functional group.
If the oxygen was like 1 carbon over, would it make it an alpha group?
No, we won't sort of be tricky like that.
All right.
If there's a carbonyl in there, it'll be the one attached to the ring.
But it would be.
Yeah, so if this thing was over here, you're saying?
Yeah.
Then it's not going, then you're gonna look at this carbon here, it's an alkyl carbon.
Okay.
But again, I'm not gonna be tricky like that. All right, so then for this last one, I have a nitro group. The nitro group is what? Orthopara or meta directing? Meta. And now I got this is kind of one of the trickier, substituents to add on here because you're actually creating a new carbon-carbon bond. So what I'm adding is these 1, 2, 3, 4 carbons to my ring. So again, I know I have a nitro group on there. I know this new functional group is going to go in this meta position here. But again, what I'm attaching is those 4 carbons, and importantly, I'm attaching it at the carbon that is at the base of that halogen, right? On that second carbon there. So how would that look? Would be this here, right? I've added these 1, 2, 3, 4 carbons. And importantly, that carbon that used to have that halogen on it, that used to have that chlorine on it, is what's now attached to that ring. Okay. This would be, if we're going to look at that list of reagents again. Whoops. This would be this one here. But again, all I've done in that problem was explicitly represented what that R group was. So instead of having RCl, I told you exactly what that was in this case. It was this compound here. All right, so then the last set of problems that we can do from this chapter is kind of the inverse of what we just did, right? Before I gave you a list of reagents and I told you, I gave you a substrate and a reagent and I said, tell me the product. Here I give you a substrate and a product and you're gonna have to tell me what reagents you use to get there. And again, the whole thing about this chapter is the order in which you use those reagents really mattered. Some of them are orthopara directors, the other ones are meta directors. So using that reagent bank, we want to be able to complete problems like this. right, so I don't want to run out of time, so let's go through these. Okay, again, you're going to be picking reactions from that reagent bank and putting them in the order that we need in order to complete this reaction here. So how am I going to approach a problem like this? I'm going to look at my groups that are being added. All right, so this one here, I need to identify which of my 6 reactions would put that group on there. So which one of these 6 am I going to be using for that?
The H2 as a whole.
The fuming, yep, exactly. So this is that one. Okay, and then I'm going to go to my other group. This is now this nitro group. And I'm going to identify which reaction I need to put that group on there. In that case, it would be this one right here. Okay, so these are my 2 reactions that I'm going to use to create that product from benzene. Now the last step is going to be what order do I put them in, right? Because the order can matter in these reactions. For this particular reaction here, my sulfonyl group is what? Ortho, para, or meta-directing? And what about my nitro group? Is also a meta-director. And these 2 compounds are sitting, or 2 substituents are sitting meta to one another. So in this particular case, it actually doesn't matter what order I put them in. Either order would be correct. So really, again, kind of arbitrary. Or you could have swapped them and that would have been perfectly okay as well. All right, for this particular case, because they're both meta-directors and they're sitting meta from one another in that compound. All right, but those would be my 2 reactions. So that's how I would answer this problem here. I would fill in my missing reagents. All right, for this next example, again, I'm going to look at each one of these groups. The nitro group, we said we put that on with the nitric acid and sulfuric acid. For the bromine, I'm going to be using this reaction here. So those are my 2 reactions that I'll be using. And the last step I got to do is determine what order they should be used in. All right, so looking at my compound, are these 2 groups sitting ortho, para, or meta from one another? So in this case, they're on opposite sides of the ring here, right? So this is a para compound. So then I got to look at each of these functional groups. The nitro group we said was meta-directing. And the bromine is going to be what? Ortho-para, right? And how do I tell that? Because this bromine has 3 lone pairs, right? So it's one of those ones with a lone pair located right next door to the ring. So this would be ortho-para. So one of these groups is a meta-director, the other one is an ortho-para director. Since these 2 are sitting para in my product, I'm going to use my ortho-para director first. If I put that one on there first, it will direct this incoming substituent to my para position. So the second step would be that nitric acid and sulfuric acid. All right, in this next example, I got these same 2 functional groups. So I'm going to use these same 2 reactions, right? But this time they're sitting meta to one another in my compound. So that means that the first thing I need to stick on there is my meta director, that nitro group. So this is an example of the same 2 reactions just being used in a different order and thus giving me a different product. Okay, so same 2 reactions, but again, the whole shtick of this whole thing is that the order in which these reactions are used will determine your product uniquely. All right, and we got time for one more here. For this one, I'm again going to look at these 2 groups, and I got to determine which reactions I use to add these 2 groups. In this case, It's these two, what we call Friedel-Crafts, you don't have to know the name, reactions here, right? One of them will add an alkyl group, and the other one will add this carbonyl carbon, what we call an acyl group. Again, you don't have to worry about the name, okay? But then the question is, what does my alkyl group look like? All right, so first of all, which one of these two are sitting para to one another? Which one of these groups is my ortho para director, A or B? A, so that means I need to put A on there first. Right, and what does that look like? This is a 1, 2, 3 carbons. And it's attached to that second carbon, which means that's where my chlorine was in my reagent. So first reaction is that. Second reaction, I again got 3 carbons. All right, and just, I know we're out of time here, so let me just put down the answer for y'all. All right, so again, like last time, I'll post this later tonight with more examples on there, so a different set of problems than what we just did for you guys to practice. And then tomorrow, or not tomorrow, whatever, next class, we will review chapter 6 material. Have a good one. Yep, have a good one. I got office hours tonight if you guys are stuck on anything.
I submitted that assignment for that homework.
Did you, like, right after you got my email or before that?
Yeah.
Okay. All right, cool. All right, I'll resend it. Yep.
Are your office hours in person or?
They're on Zoom.
Oh, okay.
If you go to the Canvas page under course introduction, there's an office hours page, and that has the link.
Okay, thank you.
Yep.